Let us start. Good morning, everyone. So you see that we had another contingency measure to take, and with a swap of the sessions. So it is not the plenary session. It is a parallel session on grid. As you know, this day is devoted to grid, with a plenary session which will take place at 11, and parallel sessions all over the day. So it is my pleasure to open this session devoted to DataGRID, which is one of the projects in Europe which are devoted to grid. On the program, in addition to the strikes and the plane problems, one of our speakers had a health problem yesterday, and so unfortunately she cannot present her presentation. This is Pascal Primet. But Pascal Primet will be replaced by a colleague, Cesc Delat, so you see that we can arrange emergency situations. And so Cesc will give the presentation, but we are swapping the two first presentations, and the first presentation will be given by Antonia Ghezali, then followed by Cesc Delat. So, Antonia, it is a pleasure for me to introduce her. Antonia works at CNAF, C-N-A-F, in Italy, and she's leading a group of doing research in the field of advanced applications on high-speed networks. Antonia, the floor is yours. Thank you.
Thank you. So, I'm going to describe the most important characteristics of the DataGRID Prototype 1 project. As François said, DataGRID is one European project aiming to build a prototype, a grid prototype, on the basis of the requirement of the European research communities. The content of my presentations is the following. I will start trying to describe the scenario in which this project is started, then the major components of the project, that is the authentication and the authorization management, the DataGRID resources, and then the DataGRID services, and at the end, a brief description of the release 1, the testbed 1, and the conclusions. So, as I said, this project collected a list of requirements coming from research community belongs to high energy physics, Earth observation, and bioinformatics community. I just describe some characteristic of the high energy physics environment experiment computing, just to give an idea of what kind of requirements this grid is supposed to satisfy. The high energy physics experiment characteristics are mainly the huge number of users. Thousands of physicists from hundreds of institutions, labs, and universities come to CERN in order to design, build, and run an experiment. The data collected from this experiment will be analyzed by distributed resources. They pool to computing, storage, and network resources to analyze a petabyte of data. One characteristic of the HAP computing is the natural parallelism based on the HAP experiments that allow to set up an high throughput computing instead of an high performance computing. Another important characteristics of these future experiments and therefore of grid are the computing resources. The computing resources will be mainly based on a cluster with a high number of PCs. The number of these PCs for each cluster, called also far, range from 500 to 1,000. So just to give an idea of how large is the community for one experiment, I saw this picture. This is the CMS experiment foreseen in the next 5 or 6 years. Is made up of 1,800 physicists, 150 institutes, and 32 countries. Also, just to give an idea how much data they have to analyze, this is a picture of the detector of these experiments, and this is just to give an idea of the data acquisition rate, and so the amount of data that at the end of the data acquisition they record and they want to analyze. These are of the order of 10 megabytes per second after a factor of 10 to 7 reduction done online. So these are already some key parameters about the amount of computing power this experiment must, not only this experiment, but all the experiments that will be built on the LAC apparatus will collect 10 petabytes per year. So all the experiments, these are 4 experiments. In order to analyze this data, they will set up a hierarchy of resources distributed around the world, and this hierarchy is also called the tier hierarchy. There will be tier 1 and tier 0 and other level of these resources. This is to have an idea of how big must be the computing power, for example, at CERN, and also in the several regional centers that will be set up around the CERN in order to analyze this data. So this is the picture that illustrates the hierarchy of the different regional centers that will analyze this data. You can see CERN, that is the center where the data will be produced, and then you will see all the country, the organization participating to the experiment that will set up each one at least one regional center, big regional center, and then there will be per each organization other level or regional center with a less size of computing power. And in the end, there will be the users with their desktop that will try to use all these distributed resources, and the model that they think to use is GRID. This is the reason why there have been so much interest from this community on the GRID model. The HAP community thinks that GRID will be an extension of the web concept, and that the GRID will realize what, concerning the computing, what the web realized for the information. So the web is now a uniform access to the information, and the GRID should be a flexible and line-performance access to all kinds of resources, and to have also the possibility to create on-demand, powerful virtual computing system. So the model of grids is defined by the author of the grids, the people of Globus. as a combination of technologies and infrastructure that enable coordinated resource sharing and the problem solving in dynamic multi-institutional virtual organization. This is what characterizes the collaboration of the DataGRID project, as I have just said. So the problem is to create something that allow this resource sharing of computing resources in a coordinated way between these several dynamic and multi-institutional organizations, also called the virtual organization. This is the goal. So the grid is not a new computer, is not a new operating system, but is a new way, completely new way to use computing resources, distributed computing resources. Another characteristic of the model that we adopted in DataGRID is that these computing resources will not be, how to say, completely monopolized by the grid, but these computing resources can be continue to be used also locally in the usual way. This is another important condition to satisfy. So the dynamic nature of the virtual organization brings the need of specific virtual organization service to authenticate and authorize the user to access the grid resources, to manage grid access policies and so on. So one of the problem is how to manage the user access to the grid. In order to access the grid, an identity certificate is needed. The user do not have a login name and password via which they can log in the grid computer in the usual way, but rather they must own an X509 identity certificate issued by a certification authority, which this certification authority must be trusted by the DataGRID project. To be trusted means that the certification authority must adopt a set of agreed rules. The certification authority publishes their certificate in a held-up directory server. This would be very useful in order to, as I will describe later, will be very useful in order to to adopt tools and automatize the authentication and authorization procedure. This is the list of the already trusted certificate authority that will participate to the DataGRID project. CERN, there is also the Department of Energy certification in US, certification authority, because there are users in US that want to access the grid, INFN, the Dutch CA, UK, CNRS, and so on, and they are continue to join, other CA are continue to join this project. The mechanism adopted concerning the authentication, the authorization and authentication is based on the global security infrastructure, the so-called GSI. GSI implements the standard generic security service application program interface based on the corresponding RFC that define the standard. This mechanism requires the ability to pass user, host, and service authentication information to a remote site so that the further authenticated connection can be established. This is the reason why we call one-time login. So when you connect once, then you can continue to use the grid, the grid resources without to log in another continuously. Proxy is the entity empowered to act as the user at the remote site. The remote sites is able to verify the proxy certificate by descending the certificate signature chain and thus authenticate the certificate signer. The signer identity is established by trusting the CA. That is the reason why not all the certificate of every CA is accepted, but it is very important to have to join the trusted CA. The other characteristic of the proxy certificate is that it has a short expiration time. The default value is 1 day. The last step of this process is the user authorization. All what I have just described is only to authenticate the user, and then you have to authorize it. The user access is granted by checking the proxy certificate subject, the X500 distinguished name, and looking it up in a list, the so-called grid map file that is maintained in the remote site. So in each remote site there will be a grid map file that link the distinguished name of the user certificate with a local ID, user ID. And in this way, the user inherits all the rights of the local user. Many distinguished names, so many users can be linked to the same local user. But this is the process in the way you are authenticated and authorized. But the real authorization is specifically granted by the virtual organization which the user belongs to in agreement with the owner of the grid resources. This is what has been developed by DataGRID in order to have a grid that is also manageable. So we need to do this, we need to have server, management server and tools. This is the process that I have just described, the requesting a user certificate, then the proxy certificate that is built online, and then is the local site that check the proxy certificate, is able to know the CA authority, the certificate authority that has assigned the first certificate, and on the basis of this CA, if this is a CA trusted by the project, by the grid, then the ZDN, the distinguished name of the user, is looked in a grid map file, and if is found the association between the certificate and the ID, the user can use the grid. So to manage all this access to the grid, each VO must set up an LDAP directory containing all the users belongs to the virtual organization, the certificate of this user, and in this way it is possible to generate in an automatic way the grid map file of each that must be in each computing resources of the grid. Okay, this is the picture that illustrates the grid map file generation, starting from the VO LDAP server for each users. The tool make grid map, will check the certificate, and will check also the grant to access the grid, looking at this other authorization directory that has been built specifically for DataGRID testbed. So this is concerning the access to the grid. Now I try to describe which resources and how they are managed are in the DataGRID. DataGRID fabric, so the resources of the grid, consist of farm of centrally managed machines with multiple functionality. They can be computing element, worker node, storage element. This machine can be also configured as information service and so on. So in each site there is a server containing all the software and the profile that has to be that defines all the resources of the grid, and in this way, in each center, you can automatically configure all the resources that you want to set up in your center. This will be more clear later when I will speak about the release of DataGRID. But here, just to have an idea that in each center you have a server containing the software and the profile, and in this way you can automatically set up all the grid resources, computing element or storage element or other things. So, as I said, the computing element identify large computing farm of commodity PCs. The access to this computing element is based on the Globus Resource Access Management Service, the GRAM. This is a already known protocol adopted around the world in order to access the grid resources. This service is responsible for operating a set of resources under the same site-specific allocation policy or local resource access management, like LSF, PBS of Condor. The storage element identifies any storage system with the ability to provide a direct file access and transfer via FTP, NFS, or other protocol using the grid security mechanism. So the Grid Information Service is one important service of the grid. It plays, as I said, a fundamental role in the DataGRID environment since resource discovery and decision-making is based upon the information service infrastructure. Basically, one information service is needed to collect and organize in a coherent manner information about grid resources and status and make them available to the consumer entities. ADG Release 1 adopted the Globus Information Service, MDS, which is based on a LDAP directory service. The advantages of this choice of this MDS is that LDAP is a well-defined data model, standard consolidated way to describe data. It has a standardized API to access data in the directory server. In order, allows a distributed topological model. But the disadvantage that is very important for a grid is that LDAP has not been designed to store dynamic information, such as the status of the computing, storage, and network resources. For this reason, other mechanisms are already under developing and under test within the DataGRID project. But for the first release, MDS has been used. This is the GRAM architecture, the protocol that allows to submit jobs to a computing element. In this architecture, the fundamental services are the gatekeeper and the global security infrastructure along the authorization and authentication that I have already described. If the user is authorized, then a job manager is created in order to submit the user job to the local resource manager. A GRAM reporter continuously query the current status of the resources and store all the information to the MDS. So a DataGRID made choices concerning the local resource manager. As I said, the DataGRID uses mainly LSF, but also PBS and Condor is used as local resource manager to manage all the PCs of the farms. and also developed its own information provider in order to report the specific information to the MDS used by the scheduler that I will describe later. So ADG also developed a specific schema for its resources. What is the schema? The schema is a data structure describing the grid resources and the status, and they represent what makes data valuable to the grid tools and applications. As I said, DataGRID defined its schema. The reason is because in Globus only the CA schema was present, storage element and network element schema were not present, and moreover the computing element schema defined by Globus was not suitable for the DataGRID specific computing resources. DataGRID consider a computing element as a queue, that is since decided that the queue is the most suitable data structure to model a cluster of homogeneous species. The definition but I want to emphasize that to have a standard schema for all the grid resources around the world is very, very important in order to make these resources usable and interoperable. So the definition and the standardization of the information about the grid resources is largely work in progress within the Global Grid Forum. And moreover, not only, but there is already some activity, some work is in place in order to define a common schema for computing element, storage element, and network element between the DataGRID project and another project that is just started and is mainly focused on interoperability. It's an European project and works together with DataGRID, and they partnered in US that are represented by this project, IVDGL, it's called the Virtual Data Grid Laboratories, and Globus. So this is very important for us because it will allow access to US and EU grid for both EU and US users. So this is an important aspect to take into account and to develop. Scheduling on the grid. This is one of the most important aspects of the project, of the DataGRID project. The so-called workload management of application dealing with large amount of data and cluster with high number of machines. The scheduler is the most critical component of the resource management system, since it has the responsibility of assigning resources to job in such a way that the application requirements are met, and of ensuring that the resource usage limits granted to the user are not exceeded. This is the goal of the workload management within DataGRID. Well, scheduling is a traditional area of computing research, of computer science research, but scheduling on the grid is totally new, difficult to implement scheduler with a specific characteristic. Which properties should have the DataGRID scheduler? Here I listed a number of property and requirement that the implementation of DataGRID scheduler as follows. One is that has to take into account of the distributed organization. So the need is to have not a centralized scheduler, but rather a community scheduler. So it's been built in order to be easily duplicated in order to satisfy different virtual organization needs. Another property is the predictive state estimation in order to deliver adequate performance even in face of dynamic variation of the resource status. In a grid environment, the The variation of the resource status is a common parameters status, so you have to take care also of this particular characteristic. Another requirement is the ability to interact with the resource information service, the information service that I just mentioned. At the moment, all the existing schedulers require that the user specify the list of the machine that he has permission to use. But in this case, in this grid, we want to make something is more efficient and more automatic. So the scheduler, the grid scheduler, has to use the information system. Then has to have also the ability to optimize both the system and application performance, depending on the need of the data grid user. At the beginning I said that the high energy computing is a high throughput computer rather than high performance computer, but within DataGRID there is also the biology community that needs high performance computing. So the scheduler has to adapt to the different requirement of the application performance. Another important characteristic, of course, is the submission reliability and must guarantee that the job can be, even if the results disappear during the job must be automatically resubmitted. Then also there is another characteristic is the allocation fairness. As I said, the grid resource is not only used by the grid, but continue to be used also by the local users. 2 minutes. Oh, sorry, I have to go quickly. So having in mind these properties, the implementation, the workload management implementation of release 1 is consists of the following service, of the following component. First of all, the resource broker. This is the core component, which has to find the computing element that best matches the requirement and the preference of a submitted job, considering also the current distribution of load of the grid. Once a suitable computing element is found, the broker passes the job to the submission service for the actual submission. This task includes also the interaction with the DataGRID management service to resolve logical dataset name, as well as to find a preliminary set of sites where the required data are stored. The scheduling of the job in DataGRID take into account the distribution of the data. This is another important parameter that the scheduler has to take to consider. Other components, the logging and bookkeeping, follow all the activity of the job. Another important component is the user interface. The job is submitted using all the function of the ADG user interface, that the description of the job is expressed in the job description language. This is the language defined by the DataGRID in order to describe all the requirements of the job. I go quickly. This is an example of DataGRID job submit, where you can specify all the parameters of the job that you want to specify. As I said, the most important one is the data location. This is another. I have no time to explain. These are is a list of the user interface commands that the user can give to the grid. Submit the job, selection a list of suitable resources, cancellation of one or more jobs, retrieval of the output file, and so on. This is the picture describing the job submission process. So the user with the certificate and using the user interface at its desktop submit the job to the resource broker. The resource broker look for information to the data management service, to the information service, and in order to find the best match between the job description and the grid resources, and then submit the job to the selected resources. When the job is finished, all the output, that is called output sandbox, is returned to the user in this way. Here you have the logging and bookkeeping and so on. Then there is also data management. I have to stop. I go only through the data management architecture. I want to say that it's important that DataGRID adopted for optimizing data access and providing fault tolerance data replication. So data management is based has to deal with data replication in a very efficient way. So here you have all the building block of the data management, and this is the architecture of all the components dealing with data replications. And what is very important is the replica catalog that for each logical file maintains all the copies of the physical files. And this is the service contacted by the broker in order to know on the basis of the logical files. So,
okay,
I'm sorry that I have not measured them.
Okay, I think that you've produced a paper which is available on the web proceedings, and in particular the details, in particular on the data management, you had to skip at the end. But I think that we thank you for having given us a quite good and detailed overview of the major building blocks, technological building blocks of the DataGRID project. So let us thank Antonia. We will group the questions at the end after the three speakers have delivered their presentation. The second presentation, as I said earlier, cannot be given by Pascal Primet because Pascal is ill, and Cés Delat has spontaneously and courageously accepted to give on the spot the presentation using Pascal's material. Cés Delat is with the University of Amsterdam. He runs research projects on topics such as policy-based networking, AAA, and Cés Delat currently co-chairs the IRTF research group. IRTF means Internet Research Task Force. This is complementary to the IETF, and he runs the group on AAA architecture. So as long as the laptop is connected, Cés will deliver his presentation.
Notebook, yeah. And I need to do detect displays. Yeah, there we go. But the application PowerPoint has grid, that's very nice. Of Microsoft. You see, disasters never come alone. So there it is. My name is Cés Delat, not Cés, but that's probably the French pronunciation. You are going to see these slides for the first time. Well, be assured, I've seen them for the second time. I got, well, yesterday Pascal more or less collapsed here in the conference, but I can assure you she is fine again, but she needs to recover and get her strength again. So there's not, she couldn't make it, but it's also not too bad. What I'm going to talk about is about work of work package 7 within the DataGRID project, and I'm sideways connected to that. Since a year I work at the University of Amsterdam, and the University of Amsterdam, Sarah and Nikev are partnering in Work Package 7, and my group has worked together with those people mostly on the monitoring area, but I have sat in all the meetings, and that's why I hope and think I can at least lead you through this presentation. I must say, just like the previous speaker, this presentation contained about 40 slides, and I managed to just cut them down to about 30, so let's see where we get. So this is the one which I at least adapted. The European DataGRID project. The European DataGRID project is in fact a kind of grid project which aims to provide a production or a computing environment for three application domains. There were three domains which joined together and proposed the DataGRID project to the EU. And obviously that is, as usual, the high energy physics community, but in this case also the biology and medical imaging community. There are also some organizations from that field in this project, and Earth observations. And also in the Netherlands we have the weather forecast people, the KNMI, involved in the Dutch grid. The European DataGRID project is a partly funded project by the European Union. There is a massive unfunded part and parts which then are funded by the European project, and you will later find out that the networking tasks, the Work Package 7, is only for 10 or 20% really funded, and the rest is funded either by the organizations themselves or spare time of poor people. The European DataGRID project is supposed to run from January 2001 till December 2003. So next year, December, this project ends. There is a parallel project which was put in the EU for funding, and which started at the 1st of January of this year, and that is the DataTag project. The DataTag project is way more future-looking networking project actually, and also aims at interconnecting the European and the US grid project. So in that project we work, and there I'm very active in, we work on lambda networking, on high performance, long delay throughput networking, getting specialized links between the US and Europe, and on cross domain authorization authentication problems, because you have Americans who want to work at CERN, for example, and you have people in Europe who want to work at SLAC or at Fermilab. So there are all kinds of problems then. So the partners in the European DataGRID project are CERN, CRNS in France, ESA-ESSER in Italy, INFN in Italy, the NICEF is a principal partner in the Netherlands, and PPARC in the UK. And apparently from all those groups in Work Package 7, I'm the only one here. European DataGRID projects. There are about 7 applications distributed among 6 virtual organizations. There are 11 organizations in 15 countries. There are about 40 sites which, if you look to all the organizations and applications working together in this DataGRID project, there are 40 sites, either institutes, computer resources, laboratories, universities, in 40 sites in Europe which have to work together, or want to work together, I better hope and say. So based on the European, the interconnectivity of those institutes is obviously not delivered by the DataGRID project, but the DataGRID project makes use of the also partly European funded European CERN backbone, and of obviously the various national research networks. So this is a picture which you probably will see more often in this conference, because this is all about European national research networks. But I had a pointer. You see here, obviously, those red dots are the different organizations which are working together in this so that there should be 40 dots. I didn't count them yet, so you may do that. And you see here the main interconnection links of the GEANT backbone. But obviously, from the grid point of view, when you have your distributed computer resources, your distributed storage, and your so when you have those elements, then what you really care about is, of course, the connections you see between the different resources. So you have laboratories with the resources, and what you care about is how fast do I get from this point to that point. And actually, in the grid, you do not see the topology of the underlying network. But the performance you get from this point to that point, or from any participating site to any other participating site, is of course important to know how you map your calculation problem to your computing resources, storage resources, visualization resources, and your network. So all those elements come back in what I later will explain as a cost function. A cost function which you want to optimize your output, throughput, or whatever you want to put. So what are the activities in Work Package 7? There are, if I remember well, 4 tasks. Well, the first task is an obvious one. It's working together to get a technical collaboration to provide the interconnectivity between all the participants. I mean, there's of course no way that with almost no funding this could really buy lines between sites which are poorly connected but which want to work together. So the Work Package 7.1, the task 7.1, is about collaborating with the local NRNs and Dante to get the connectivity between the sites which is needed by the applications. So it also includes getting the requirements from the applications, and a long study was done last year, and that result comes back a bit later, I think, is in Deliverable 7.1, which you can find at the website of this project. In order to really test if, we get requirements from applications, you also want to know if the network can deliver what applications are asking, because many applications are asking throughput and bandwidths and data transport capabilities and storage capabilities, which they don't need today, but they will need when their detector comes online or when their experiment starts, and so on. So we have also put machines, and we are discussing with Dante and with other bodies, to put machines in place so that we can at least already test how far that the network goes in meeting the demands which the applications have. So task 7.1 is mostly about that. Task 7.2 is about QoS. So it is about reliable multicast, high-performance transport protocol. That's something different, by the way, but QoS services, so premium service or scavenger mode services. So in those cases where throughput between different parts of that grid is not met, the requirements are not met, putting quality of service measures in place to meet those demands. Obviously, there is then also a political willingness needed to provide this extra quality of service to this project, because then inevitably somebody else is going to suffer unless you do scavenger mode. Well, scavenger mode is actually very interesting, because scavenger mode allows, for example, heavy users to start their enormous file transfers, which are normally bogging the network and hurting other people. In scavenger mode, you don't care if they start. I mean, normally you would say, well, you start your dirty thing somewhere in the night, then it doesn't hurt us. But with scavenger mode, you can say, well, you start anyway, as long as you do it in scavenger mode, because if you are hurting us, your packets are dropped first. So it doesn't hurt people. And that's a very good reason to put scavenger mode in place. So one of the more recent, very interesting work which was done and which was shown 2 weeks ago, the tsunami protocol between Seattle and Brussels, where they transported 700 or 800 megabit continuously. They did that in scavenger mode, and it was UDP traffic. Normally UDP traffic kills your networks, but not if it is in scavenger mode, because this is first traffic you can throw away, which you probably already do with UDP, but that's at the side. So task 7.2 has 2 main things. That's all this QoS stuff, which we are doing already for 5 or 8 years, if I remember well. The other thing which is extremely important nowadays is the high-performance transport protocol work. TCP was designed when the networks were about a factor of 1 million slower. If you go back to 1982, you had about 900 kilobit. That was high speed if you had that. Now we are talking about 1, 2.5, and 10 gigabit links between the USA and Europe. And my group has actually a 2.5 gigabit transatlantic line for only research purposes. If you want to work with those lines, you find out that TCP is now getting into trouble because of the round trip time and the protocol and so on. So a lot of work needs to be done there to get new protocols which can really fill pipes efficiently if you know that the pipe is only yours. I mean, if you have to work in an aggregated field where in the internet, so in the internet at large, then you need to be a little bit proactive, that if you see that there is congestion, you need to slow down. But if you know that the line is only yours, then you can, of course, be asocial with your protocol. Task 7.3, I will speed up again, is a bit about network monitoring. See what's happening in the network and providing the information for the grid scheduling algorithm so that they can know, oh, we shouldn't do that storage and that CPU because it is very busy there. We can better use a slower cluster somewhere else, but we have more connectivity, for example. That's kind of optimization questions. And task 7.4 is security. So about integrity, authorization, authentication issues. Obviously, there is a collaboration with Dante for the test of IP premium. That's better than best effort. I said we can also try to get worse than best effort, which usually is not too big a problem. And we are in the backbone currently putting machines, or at least we are agreeing with Dante to put machines in several POPs to test, for example, over-provisionedness and different schemes. My belief actually is that the problem is usually not in those 10 gigabit backbones, but way more in the edges where you get a lot of aggregation and at the university and more at the local sites. There are way more problems there than in the core. But yeah, the core is small, so it is easier to work with that, obviously. Network provisioning, there have been network requirements studies. How am I doing? Okay. Not okay, actually. There have been network requirements studies. There have been application requirements. They have been collected. The physical networks are identified which we have to work over. And you see that whole giant is multiple gigabit backbone nowadays. One big question in the beginning was, is a virtual private network necessary for the DataGRID? Or can we run over just research networks? And the conclusion was that we don't need VPN services to run this. You just run on the open end-to-end network, and well, you can find that in deliverable 7.1, which you can find on the DataGRID side. This shows you a bit. Well, this doesn't show you a bit. Okay, look on the slide. Look on the web server. But there's a table which shows you the information we ask from the applications. So we ask how many megabits do you want? Is it burst size or is it continuous and so on? And sometimes you get interesting results. One interesting result was that for example, one of the big detectors at CERN told us that they need so much data per year and that it is on average. So then I take that data and divide it by the average number of seconds in a year, and then I found, well, they need about 10 to 100 megabits, so that shouldn't be a problem. But then it turns out that it is bursty, of course, and they want to do this in a week, 1 week every 2 months. Yeah, okay, then it gets a problem. So you see some of those numbers in this slide. So let me go on. Network performance measurements. It seems to me sometimes that most of the traffic which is going on the network is ping and hyperf and all these things. And obviously you have in DataGRID you have n participants, so you need n times n minus 1 if you want to know really all the interconnectivity. But you have of course also other projects which for their purpose also ping around. So sometimes I get the feeling that there is a lot of pinging going around, which is also a little bit worrying, because there is indeed a large fraction of just monitoring, user-side monitoring going on these networks. But we need, if you really want the grid to work and you really want to be able to optimize all the resources, you need to treat the network elements, so the network as also a kind of resource which you can configure and use. You need also to be able to get the metrics to judge which part you would use. And that's what you see written here. Network performance parameters are used to optimize resource allocation for your complete problem. So let me skip here some things. Actually, most of this work you can find. There are now 2 deliverables. They are online, and you can find them on the DataGRID site. This is the network monitoring architecture, which is currently brought up and in place. We have a kind of layer where we have all the tools sitting, which can give us information. So either single trip time or round trip time, so one-way delay or round trip time. The data is collected, it is put into LDAP servers, and then the grid, the grid resource managers can use that data in their decision taking of which resources for a certain submission to use. You also see that there are 2 types of monitoring tools. You have either what I call the external tools, which, like Pinger or like iPerf, but there are also some implicit measurements, like you see here, grid FTP, and that is actually that there are some numbers we get from grid FTP applications. If an application transports data from A to B, then grid FTP also gives the numbers how fast the transport went, and that is also used. But obviously, you only get these measurements if just somebody was running there. So only if an application used grid FTP, then you get also the number of how fast that went. While the other tools you can run, of course, on demand. Also, a study we are doing is getting information just from the routers, their packet counters and their counters, their monitoring counters in routers and switches. So there are active methods and passive methods. I just explained that. One problem is obviously that at every location everybody puts his or her measure box at the most optimal place. So where's the most optimal place? Where the gigabit link comes in from the backbone. They have a huge switch, and we have a spare gigabit port, so there we put our monitoring. And then we have 100 megabit that goes to a hub, and there we have our grid. So obviously what you are then measuring from this box, which is very well backbone connected, is not what your application sees. And that is also sometimes a problem which you see here. Here you have resource, but here's the measure box, so what are you measuring? So it is also very important to really know what you try to measure. So here is a list of the tools which are used: Pinger, iPerfer, UDP, Mon, Map Center, Network Weather System, and all these kind of things, and RTPL, which is developed in our group. But all these forecasting tools have one problem. At the moment you use the forecast, it is not valid anymore. I mean, it is something like if it says it is sunny outside and go outside, then I can usually count on that it is sunny and not that it starts to rain because I'm outside. But if you get the forecast, well, it is quiet on the network, so you start to use it, it is not quiet anymore. So using the forecast influences the forecast. Here are some results which you cannot see anyway from the audience, so you have to download the slides yourself. So the schema, all the data is going into an LDAP tree, and it is retrievable from that LDAP tree. Network cost functions, that's now also a big problem, because if you are going to make a network cost function, you need two things. You need, of course, the metrics, what you are going to put in, and yeah, what is the cost of a network? Is high throughput a low cost, or is a short round trip time a low cost, or is the actual cost of the network, should that go in the cost function? So that are questions. So it is not, and the other problem, okay, that's the second problem, is what constitutes a network element? I mean, is a network element just the port and the part of the network you own behind that? Or is that a concatenation of all the network elements? So the line from your point to somewhere else in another country, the port just to that resource you want to use. What constitutes a network element, and how should you deal with network elements? Are network elements domain restricted, or are they end-to-end links where you attribute the cost to? So that is also still a study in progress. So this I'm going to skip. This I'm also. There is a site where you can see how the connectivity is. For that you also need to download the slides to be able to read that, I see. So, so the main work is currently going into quality of service protocols, installing DiffServ on various nodes, and then try to prove that if you use differentiated service or premium service, that really the traffic goes better than if you don't use QoS for your application. Sometimes we even find that if you enable QoS, that your traffic gets a little bit worse. That was surprising, but it turns out that if you turn on QoS in routers, then they put extra queues in place in front of the queues where you would go in already, so you add a little bit delay. So by enabling QoS, you introduce new queues, which make it a little bit worse. So sometimes you get surprising results by enabling QoS. And of course in the transport area, looking into high performance transport protocols. This one I'm going to skip. This is just about DiffServ. So where's Work Package 7 collaborating? Obviously Work Package 7 is now heavily collaborating, or better to say, there are for 90% the same people which are doing Work Package 7 and which are now in the European Data Tech collaboration, but there we are at least funded. So we are collaborating obviously on QoS, on high throughput study and long round trip huge bandwidth links, and obviously network monitoring and measurement. So Data Tech is more or less taking over the monitoring tools from the DataGRID Work Package 7 and now deploying them cross-Atlantic. Obviously we are heavily involved in the Global Grid Forum, and many people of the Work Package 7 are actually in the high performance networking research group in the GGF, and well, John Kokhoff is one of the chairs. And obviously this project is collaborating with the other grid projects in Europe, the Dutch grid, UK eScience, INFN grid, and so on. So what are the conclusions? Testbed 0 and 1, the networking functionality was here. The IP technology is currently best effort. The Géant network has been deployed, but not by Work Package 7 obviously, but by Dante in collaboration with us, supplying the requirements and connectivity so that they could know and arrange a bit where the hotspots are. In testbed 2 and 3, grid application performance optimization should take place. This cost function should come online. The end-to-end performance analysis is what we are now working on, really understanding the connectivity graph and understanding the performance the network in the grid can get. And we are in the process of working to provide premium scavenger and multicast services, so special services in that end. For more information, I ask you to go to the website ccwp7indp3.fr or just to the European DataGRID web at CERN.ch. Thank you.
Thank you, Kees. Okay, so as you have seen the logic of this session, we started with Antonia by the sort of overview of the DataGRID project, and we moved to the more specific networking aspects, and the third talk will look at the one particular experiment which will be put in place and which is being developed to exploit the next accelerator at CERN called the LHC. This experiment is ALICE, and the next presentation will be about how this particular experiment will use the grid technologies. So it is a pleasure for me to introduce Roberto Barbera. Roberto is a staff researcher in the Department of Physics and Astronomy at the Catania University. Roberto is a physicist, and he is in charge of grid monitoring within the ALICE collaboration. Yep. The floor's
Can you hear me? Okay, fine. So it's good that we had the two previous presentations, because after the Antonia's global view of the grid and the Kees view of the network needs, I will show you the application point of view, and in particular the ALICE experiment application point of view. I will show you a few slides on the ALICE experiments, why we are setting these experiments, and why we need so badly grid computing. And then I will surf the grid activities at ALICE, the past, what we did in the year 2000 and last year, then what we are doing now with our grid prototype and with the test of the DataGRID testbed 1, and then the future, the grid interoperability with our alien interface, and then I will come to the summary and conclusions. So at CERN, the Large Hadron Collider is being built. It's a huge accelerator, 9 kilometers of diameter, and the actual superproton synchrotron will act as the injector of this huge accelerator. And there will be this accelerator is in fact a collider. There will be two beams, proton and also AV ions, and ALICE is mostly involved interested in AV ions. And there are 4 experiments already planned and scheduled to run at this Large Hadron Collider: ALICE, ATLAS, LHCb, and CMS. This is where the 2 LED beams will collide at the ALICE site. And this is how the ALICE detector looks like. Yeah, no, I have here. Yeah. Looks like. It's a huge detector, sort of 70 million different channels, and we have a time projection chamber, a vertex detector I'm involved in, and detectors for muon, for electrons, and for many other particles. And I will show you why we are building such a detector. So, which is the goal of ALICE? Oh, this is strange. Okay. ALICE aims at demonstrate the theoretical foreseen transition between the hadronic matter and the so-called deconfined quark gluon plasma, which happened in the first microseconds after the Big Bang. And we would like to do this doing a little bang using AV ions at ultra-relativistic energies, and exploiting the heating and the pressure that happens when you collide so big nuclei at this very high energies. The problem is that you don't see here, but when two lead nuclei collide at these energies, you end up with tens of thousands of particles going around in the space and producing secondary particles. So you have this is what a lead event looks like in the ALICE detector, but this is just 1/100th of a real lead event we are interested in. So we have to cope with a event 100 times more dense in the space. And actually, simulation and reconstruction of a full central lead-lead collisions at LHC, at 5.5 TeV per nucleon, creates about 84,000 primary tracks and takes about 24 hours on a top PC and produces an output which is bigger than 2 gigabytes. This is just for one event, for the simulation of one event. So just to give you an idea of, ALICE will produce about between 2 and 3 petabytes of data per year, and this is similar to 4 million today's CD-ROMs. So CD-ROM is a very thin thing, but if you pile up 4 million CD-ROMs, you end up with a pile of more than 600 meters, 2 times the Eiffel Tower. So this is the amount of data that we actually have to cope with in 2005, 2006 at the ALICE experiment. Moreover, ALICE is very spread around the world. We are setting up some computing sites where we are developing our grid activities. And actually, the ALICE grid computing sites today are spread in 3 continents, and there are several tens of sites. And in 2006, when the LHC will start this operation, we will have to cope with in the order of 100 million of events per year. The events I showed before, one simulation, and thousands of batch and interactive jobs from hundreds of users spread over the world wanting to access those 2-3 petabytes of data at the same time in a chaotic way. So this is one of the main reasons why we badly need distributed computing, and GRID could be the solution. So ALICE is going to develop a computing model, a distributed computing model. The online system, after the high-level trigger, will write on tape at CERN at the fantastic rate of 1.5 gigabytes per second. This means about 2 minutes to fill up the largest disk that you can imagine now. And this will be stored in at the ALICE Computing Center. Then the data will be replicated and distributed among the different Tier 1, as Antonia said before, Tier 1 center, in the regional center in different countries participating to the ALICE experiment. Then there will be Tier 2 centers, Tier 3 centers, department center, down to Tier 4, which are the next future user workstations. But some data will be stored at CERN, some other data at Tier 1, some other data may be simulation data at Tier 2, because the different tier centers will differ one from the other from the functionalities that they will provide to the collaboration. So, the user here wanting to analyze data maybe has to take data from a Tier 1 or a Tier 2 from the next Tier 2, or from another Tier 2, maybe the database containing data is distributed. So you end up with a real web of connections, and the grid philosophy is just the way we want to solve this problem. Well, grid activities analysis started in late 2000 and 2001. And at that time, we were able to set up a machinery like this. We had a manager site, and then we had a software repository and the installation and update of the software from the software repository to the manager site was automatic. Then we had several farms running Linux and MRTG as a monitor for disk, CPU load, and so on. And we had a RAN database, a bookkeeping database, and we were able to use Globus through a web interface to store the RAN on the RAN database. Then the information on the job to be ran was sent to the Linux farm. The job and a cron job mirrored the RAM database in several places inside the Alice collaboration. Then data were written on disk or on tape on Castor and HPSS at CERN and at Lyon. And we had the local site managers who through the web could monitor both the RAN database and the Linux farm. And this could also be possible from everywhere in the world because we were using a web interface. Any Alice user was able to mirror the status of the production, to see the jobs running on, the status of the jobs, and retrieve the jobs for subsequent analysis. So this was well before the start of the DataGRID project. Okay, at that time we had the web interface to log into the grid and submit jobs. Web interface for Globus job submission. We had a well-suited monitoring system for CPU load, for disk space, for network availability between the different sites. We had the run the bookkeeping database with the different runs, the submitter, the machine which was executing the job, the status of the job, start, stop, and many other information on the location of the final of the output files. And even at that time, we had an LDAP server managing the Alice certificate, but this was just in Italy because INFN already developed such a tool to store and retrieve the user certificate. Then, late in 2001, we moved to Alien, which stands for Alice Environment, Alice Grid Environment, which is our grid prototype. So Alien is a portal, but it's more than a portal. It's an environment where Alice user can submit jobs, can store the information on the jobs produced, and can also do interactive analysis. So the architecture Alien is written in Perl and uses SOAP for communication between services. And it's based on a web interface and a command line interface. So you can do commands, and you can also interact with the files through the web. And we have also a C API that can be called from our simulation program. And then there is a system of distributed catalogs based on MySQL or on any other SQL server. And these are database containing indexes to files, so that we replicate a real file system, virtual file system distributed across the collaboration. We worked a lot on the authentication. At the beginning, we had the AFS, so the Kerberos authentication. Then we had special token, SSH, and now we incorporated the Globus GSI, the Globus Security Infrastructure, so that the user can use their own certificate to log to Alien and submit jobs and do analysis. And everything is taken care by the system through the local PAM libraries. And this is most important, user never acquires the real password. Passwords are streamed to the local token, so user doesn't. There is the minimum risk of hacking password in Alien. And with Alien, actually, in November 2001, we did the first large production of simulation, of simulated events, as the one that I showed before. We simulated kind of 6,000 events for a total amount on disk of kind of 10 terabytes on almost 10 sites spread all over the world: CERN, Lyon, Ohio Supercomputing Center, Lawrence Berkeley Laboratory, NICEF, Torino and Catania, Padova and Bari, some sites in Italy. This is the division of the total amount of events produced in different sites for PP and LED, and this is the total amount of CPU involved in this site. So we really managed to have a prototype which allows to do distributed computing, uniform access to the Alice grid, and interactive analysis. Concerning analysis, what we are using, and we would like to use an interface with the grid tools, is PROOF, which stands for Parallel Routes Facility. ROOT is our object-oriented framework on which we based the whole Alice offline software. So imagine that there is the analysis user wanting to do interactive analysis. So it does some selections on some database containing parameters, and establishes some tags, some tags for the events that he wants to analyze. Then there is a relational database which contains the correspondence between the logical file names the user wants to access and the physical file name, the locations where those files are stored on different storage elements inside the Alice community. Then PROOF will split the job among the different CPUs in one site. It will split the process in different sub-processes automatically, and you can already execute the different jobs in different CPUs. And also, PROOF also managed to do load leverage, because I mean you can redirect jobs from slower machines to faster machines. Then PROOF takes care of merging all the outputs, merging all the histograms, all the data, all the objects at the object level, because this is our C++ objects, and the data are transferred back to the user console, and the user can do interactive analysis. This is possible right now, but this doesn't involve the DataGRID tools. Well, in December 2001, and let's say this year, the first version of the DataGRID middleware came in. So we tried to interface our environment, which was already used for real production, to the DataGRID, to the DataGRID middleware. And actually, Alice managed to set up a LDAP server for its certificates. We have LDAP server seated at NICEF, and we have a manager which introduces all the certificates of the Alice users. This is mine, for example, and you can browse from the web. You can browse the certificate, the expiration date, and everything. And we also managed to set up a replica catalog, which is one of the most important things, as Antonia said in her talk, of the DataGRID architecture. I mean, the database where logical file names are mapped onto physical file names, so that when a user has a file as an input file, the replica catalog will provide the resource broker with the information on the location of which this file is. So this is, again, something that all the virtual organizations have to do, and Alice did. We have actually we had two replica catalogs, a production one and a test one, so one at NICEF and another one in Cagliari in Italy. And actually, we were able, soon after the release of the test bed at the beginning of December 2001, we were able to run the first event on the grid and reconstruct the first event on the grid, on the DataGRID test bed. And now, we even managed to set up metadata catalog based on Java and Spitfire, which are tools provided by the working group, with the in DataGRID working group interested in data management, and we have a metadata catalog which contains all the rents of the jobs, the Alice jobs, which are submitted overnight with a cron job to all the computing elements of the DataGRID testbed, and this is the results of the status of the job. So we monitor the stability of, we automatically monitor the stability of the testbed, and we also have a metadata catalog which can be used with the next version of the DataGRID middleware for real purposes, for real production purposes. Well, DataGRID is not the only grid project in the world. Actually, I mean, US and Alice is involved in, I mean, we have US laboratories involved in Alice. In the US, there are all other grid projects, and a concern, an issue inside the European, inside the high energy physics experiments is the possibility to operate seamlessly in Europe and in US, so that US colleagues can submit jobs to Europe, to European facilities using the DataGRID services, and we can submit jobs over there using the grid services of the American grid projects. So the future is to interface our grid environment with the different grids, and uses it as a metagrid. So we have the alien user. The idea is to have the alien user interface. So you have the user wanting to access the data, and we have now the alien stack. This means all the alien services are already in place to access the data and distribute the data over the world. Then we would like to have the IVDGL stack, I mean the alien interface to the IVDGL services to access data in US grids, and the EDG stack interface, the EDG services to access the data produced in Europe. So this is what we would like to put in place. We would like to use alien as job submission, control, and monitoring. Then the application is AliRoot, our simulation package. And the data catalog is alien. We would like to parallelize job using proof, the tool that I showed before. And we will use also proof for data persistency to save the objects on files. Then we would like to have the root, AliRoot, and alien will interact with the alien services via command line or web interface. And they have to interact in the same way with the different services of the different grid projects. This is another animation. So user spawns different alien jobs. Then the DataGRID resource broker will take the job and execute the job on a computing element and then on a worker node, accessing the files both from the alien data catalog as it is and from the metadata catalog provided by the DataGRID project. Again, an Alice farm running proof or any other job manager can access on the same way the same kind of jobs, and this has to be done also by a Condor G, which is the way the American grid projects which is the tool the American grid projects want to use to submit jobs to the grid. So the idea is to have a common interface and use the EDG resource broker, the generic Alice farm, or American testbed as possible and completely independent and equal queues to submit jobs. Another thing, we want to access, as I said, the metadata catalog and the alien data catalog, and we want to be able to submit proof jobs in parallel on different DataGRID computing elements, so that and save files on different DataGRID storage elements. So we would like to use DataGRID computing element as proof nodes and use DataGRID storage elements as repositories for our files, and those files must be visible both from the alien data catalog and from the EDG metadata catalog. So this is something that we plan to implement during this year. Okay, summary and conclusion. So the huge needs of computing resources and storage needed by Alice makes the grid computing not only a very nice computing science exercise. For us, it's a condition sine qua non to access data. So we are really interested in grid computing, and we really want to implement distributed computing environment using grid technologies to access our data. If not, thousands of users could not access the data in a few years from now. We will produce petabytes of data, and it will be quite impossible to analyze those data. And for this, grid activities at Alice started very early, I mean, during year 2000, and in overall this period, Alice's attitude has been very positive and propositive. We realized Alien as our use case to show to the middleware developers how we intend to access data, to replicate data, and to analyze our data in a chaotic way. So we are not just waiting for the grid services as they will come up from the different grid projects, but we have our own way, and we want to interface different grid services. And let me make some advertisement. If you want to see Alice jobs really running on the grid, you can step out of the room and go to the DataGRID stand managed by our colleagues of the National Research Council in Italy, and you can see how we can run Alice job on the DataGRID services through the web right now. Thanks.
Thank you, Roberto, for this. Thank you for this very practical and tangible example of using grid technologies. I'm afraid we have no time for questions because, yes, it's 10:40. Our three speakers are available. There is a stand outside. I would just conclude this session by just a short comment. What we have seen here is that the DataGRID is one step towards building a worldwide computing infrastructure for the next accelerator at CERN, the LHC, and Alice is one of the 4 experiments that will use this accelerator. Now, after about 10 years, probably, of exploitation of these 4 experiments, we will have accumulated an aggregate of about 100 petabytes. Now, 100 petabytes, what it is? It is 10 to the 17th. It's quite a big number. We are not accustomed to deal with these big numbers. And last night, for preparing this session, I tried to look to the web, on the web, to try and see whether we can find a sort of equivalent. I found none, but I remember what I learned many years ago at the university. And 10 to the 17th is exactly the number of seconds elapsed since the origin of the universe. Which means that this number of bytes we'll have to handle is exactly the same number as if every second since the origin of the universe, 1 byte would have been stored. And those data have to be made available to, well, 10,000, 15,000 physicists spread over the world. Well, this is a challenge, and those people are facing this challenge, and we are pleased to see that some concrete steps, in particular in Alice, are being taken in that direction. So let us thank again our three speakers, and we have the plenary session in this room at 11. Thank you.